Generating functions, they are very important in mathematics as well as in probability theory. So not all generating functions that we will be discussing today. We'll confine ourselves to only one generating function, that is called probability generating functions. So by definition, this function generates probability. So first we have to know the definition of the probability generating function. Then how we can find the probability or extract the probability from this generating function. And we will be also discussing the property, the important property, that if two random variables having same probability mass distribution, will they have same probability generating functions, or the converse, that is, if they have same probability generating function, are their probability mass functions same? So this is called uniqueness theorem, that will also be discussed. We will also try to figure out or try to find the expression for probability generating functions for different random variables following, for example, geometric distribution, binomial distribution, or other discrete type of distribution. There are basically two main advantages or two areas where we can use this probability generating function more conveniently. The first one is to compute the moments. How to find the moments using probability generating function. The other is how to find the distribution of some n number of random variables. Now one interesting result, when this n is itself random, will also be discussed. That means number of random variables is random itself. So in this case also we will find or we will figure out the probability distribution by probability generating function of this sum of n random independent random variables. Generating functions are widely used in mathematics and they play an important role in probability theory. So it is very important to know generating functions, a few especially probability generating functions, moment generating functions. In this lecture, I will talk about probability generating functions. So first we want to define what do we mean by generating function. Consider this function as, which is a function of s, is a0 plus a1s plus a2s square plus a3s cube and so on. This is called a generating function of the sequence an if this function as is convergent for all s belongs to minus s0 to s0 for some s0 greater than 0, and this s0 is called the radius of convergence. So this is essentially a convergent series, and from this convergent series we can find the radius of convergence too. Let x be a non-negative integer valued random variable, and just denote probability x is equals to j is pj. Then just corresponding to the similarity of as, if I define ps as p0 plus p1s plus p2s square plus p3s cube and so on, in a summation formula sum over j from 0 to infinity p to the power j s to the power j, then this is called PGF of x. PGF means probability generating functions. So by definition this function will generate probability. How? We will be discussing it later. Now if you see the form of this PS, it says j from 0 to infinity p to the power j s to the power j. So this is nothing but expected value of s to the power x. Now this Pj is the probability, Pj is the probability, probability x is equals to j. So this is a generating function for this sequence p0, p1, p2, p3 and so on, and under the condition that this series must be convergent. Now if I take the modulus value of ps, mod ps is sum over j from 0 to infinity pj s to the power j, and if I take the modulus within the summation, then the quantity will be a bigger one, so it is j from 0 to infinity pj mod s to the power j, and this is less than equals to pj j from 0 to infinity that is equals to 1. We know the sum of all the probabilities is 1 for all s less than 1. Whenever the modulus value of s is less than 1, absolute value of s is less than 1, then mod of ps is less than equals to 1. So that means in most of the times whenever s lies between -1 and +1, this function, this probability generating function is convergent. Now what do we mean by p0? So if I put s equals to 0, then it's pj and 0. pj is 0 from infinity. So this is assumed to be 1. p0 is 1. Now we try to find the form of the particular this function, probability generating function, for different types of random variables. First we assume that the random variable is constant. So we say that pc is equals to 1 and pk is equals to 0 if k not equals to c. So this random variable takes only one value. Then ps will be expected value of s to the power x, and this is nothing but s to the power c. Now if you consider x to be a random variable which follows a geometric distribution with probability p, we can think about a situation where we need the number of trials necessary to get the first success, and we know that this can be modeled using a geometric distribution. Now for this, if I write the probability mass function, or the probability x is equals to x is pq to the power x minus 1. So we need x trials to get the first success. That means x minus 1 trials resulting in failures. So that's why q to the power x minus 1, and then we'll have a success p. Now by the definition of this probability generating function ps, it can be written as ps sum over j from 1 to infinity q s to the power j minus 1, because we have s to the power j, and what we are doing, we are partitioning it into s to the power j minus 1. Now the function within the summation is a geometric series, and we know that the sum will be ps into 1 by 1 minus qs. Now this 1 minus qs must be greater than 0, that implies s must be less than 1 over q. So the radius of convergence in this case will be minus 1 over q and 1 over q. So this is a geometric distribution, and this is the form of the probability generating function, and here we can also find the radius of convergence. Similarly, if I consider a binomial distribution, x follows binomial np, then ps can be written as n choose x, p to the power x, q to the power n minus x into s to the power x, sum over x from 0 to n. Now you can club p and s together, then this will be nothing but q plus ps whole to the power n. So this is the form of the probability generating function of a random variable x, where x follows a binomial distribution with parameters n and p. Similarly, if x follows Poisson distribution, the form of the PGF will be e to the power minus lambda sum over x from 0 to infinity lambda s to the power x over x factorial. So it will be e to the power lambda into s minus 1. And if x follows negative binomial with parameter p and n, then it will be just like the geometric form will be ps over 1 minus qs whole to the power n. Here also we have the radius of convergence as 1 minus q minus 1 minus q, 1 by q to 1 by q. So these are the few examples where we can find the probability generating function for a random variable. Now one interesting note is that whenever we are talking about probability generating function, we are confining ourselves only to the discrete random variables, because for the continuous probability distribution or continuous random variable, we don't have any concepts called probability generating function, because here probability x is equal to x for a continuous random variable is 0. PS is absolutely and uniformly continuous within its interval of convergence. So this is one very important property that one must remember, that the probability generating function is absolutely and uniformly continuous within its interval of convergence. Another important property is that this probability generating function can be differentiated term by term within its interval of convergence. it can be differentiated once, it can be differentiated twice, thrice, 4 times, as many times as we want within its interval of convergence. Now if I differentiate PS once, what I will get? P prime S. This is the DDS of PS. So it will be sum over j pj s to the power j minus 1. Now if I do this, this is nothing but expected value of s, and expected value of x is equals to p prime 1 if this sum is convergent, otherwise it will be infinity. Similarly, if I do the differentiation twice, it will result into expected value of x into x minus 1, once again subject to the condition that the sum j into j minus 1 pj will be finite. Now once we have this probability generating function, the definition of probability generating function, the question that we want to ask that whether it can be used for characterizing a distribution. Well, we have one uniqueness theorem. It says that if x and y, they have PGFs, PXS and PYS respectively, then these two PGFs will be equal for all s if and only if probability x is equals to k is equals to probability y is equals to k for all k ranging from 0, 1, 2 and so on. So what do we mean by this? We want to say that the uniqueness theorem says that integer valued random variables have the same probability generating function if and only if they have same probability mass function. So if they have same probability mass function, then the PGFs will be same, and if PGFs are same for all s, then they must have same probability mass function. The radii of the convergence of PXS and PYS are greater than or equals to 1. If this is true, so they have unique power series expansions about the origin. So you can write PXS as sum over k from 0 to infinity s to the power k into probability x is equal to k, and PXS as equals to k from 0 to infinity s to the power k probability y is equals to k. Now if we have this condition that PXS is equals to PYS, then these two power series, they have identical coefficients. So if they have identical coefficients, that means probability x is equals to k is same as probability y is equals to k. So this is what do we mean by uniqueness theorem. Now once we know the probability generating function, is it possible to get back to probability mass function? Because we know that if we know probability mass function, we can find the probability generating function. Now suppose a random variable x has a PGF probability generating function PS over 1 minus QS. Seeing this form, we can immediately conclude that the random variable x follows a geometric distribution with parameter p, where q is equals to 1 minus p. Now given PGF for an integer valued random variable, how to find the mass function? This is the next job, that how to find the mass function. Once we identify the function, then how to find the mass function? There are two options. First, we can expand this PXS in a power series in S and set pk as the coefficient of s to the power k. So you just expand the series pxs as a power series in S and find the coefficient of s to the power k. That will be your probability x is equal to k. There is another option. We can differentiate pxs k times with respect to s and we can put s equals to 0. So either expansion or differentiation, whatever fit suitable for the case, we can do that to find the probability mass function. It is often convenient to work with PMF than with the mass functions. This is true whenever we are talking about calculating the moments or finding the distribution of the sum of independent random variables. We'll be talking these two later. So moments and sum of the independent random variables, the distribution, finding the distribution, it's much more convenient to work with this probability generating function rather than probability mass function. Now I'll describe why. Suppose we want to find the moments. If x is a random variable with values in the non-negative integers, the moments of x are easily found from the PGF of x by differentiating the function at s is equals to 1. So I have a theorem. Let x be a random variable with probability generating function Ps. Then rth derivative of Ps at s equals to 1 equals expected value of x into x minus 1 into x minus r plus 1 for all r belongs to 1, 2, 3 and so on. So PRS, that is the rth order derivative of this probability generating function, will result in some moment. We'll give a non-rigorous proof for this result. Why this is non-rigorous? I'll describe that. What is P prime is? This is DDS of sum over k from 0 to infinity s to the power k probability x equals to k. Now if I interchange the order of summation and differentiation, then it will be sum over k from 0 to infinity DDS s to the power k into probability x is equals to k. So this is nothing but sum over k is equals to 0 to infinity, and if we differentiate DDS over of s to the power k, it will be k into s to the power k minus 1. So we are left with this form, that sum over k from 0 to infinity k s to the power k minus 1 probability x is equal to k. So if I put, for example, s equals to 1, p prime 1, we are left with sum over k from 0 to infinity k into probability x equals to k, and this is the definition of expectation. So the first order moment, population moment, can be computed by differentiating the probability generating function once and put s equals to 1. So why we are saying this is non-rigorous? In the whole procedure while proving this result, we have assumed one thing, that we can interchange the order of summation and the differential operation. But the question is that, is it permissible? Well, in most of the cases where we have mod s less than 1, this is permissible using Abel's lemma. So if I use the concepts of Abel's lemma, then this interchange is possible and this proof is quite okay. Now the next advantageous area where we can use this probability generating function is the finding the distribution of the sums of independent random variables. I'll start with 2 random variables, so we can easily extend this concept to 3, 4 or a finite number of random variables, or even random sum of random variables. We'll describe that later. So suppose that x and y are independent random variables. This concept of or assumption of independence is very crucial. So x and y, they are independent random variables, each taking the values in the set 0, 1, 2 and so on. Then if we want to find the sum of the PGF of the sum of x and y, px plus ys, then it is nothing but product of their individual probability generating functions. The proof is very simple. So by definition, pxys is nothing but expected value of s to the power x plus y, and we can write it in this way: expected value of s to the power x and s to the power y. Now since x and y, they are independent, we can write down this expected value of s to the power x, s to the power y as expected value of s to the power x into expected value of s to the power y. That's why the concept of or the assumption of independence is so crucial. And this is nothing but pxs and pxy. So the PGF of sum of 2 random variables is nothing but product of their individual PGFs. So if we just extend this concept for n number of random variables x1, x2, xn, and if you are interested about the distribution of the sum Sn, which is x1 plus x2 plus x3 plus xn of n independent random variables, each taking values in the set 0, 1, 2 and so on, then the PGF of Sn, P, S and S is nothing but the product of the PGFs of individual random variables. That means it is product of Px1s, Px2s and so on, Px and S. Now we consider another interesting result. Suppose the sum is itself random. That means how many random variables will be included in the sum is also a random number. So now I have x1, x2, x3 and so on be independent random variables, each taking value 0, 1, 2 and so on. And if all these xi's are identically distributed with common PGF, we have one common probability generating function Pxs, then it is interesting to find the PGF of the sum Sn, S capital N, as x1 plus x2 plus x capital N. Now this capital N is a random number. It has some distribution. So we cannot prefix it to a particular number. So under this circumstance, the probability generating function of Sn, Psns, is Pn of Pxs. This is called convolution. Now the suffix are very important. Its Pn means we are talking about the PGF of the random variable n, and Pxs we are talking about the PGF of x. So this suffix will tell for which random variable we are computing the probability generating functions. How to prove this? So Psns by definition is expected value of s to the power x1 plus x2 plus xn, and this capital N is random. Now using the concept of conditional expectation, this expectation can be written as sum over small n ranges from 0 to infinity, expected value of s to the power x plus x1 plus x2 plus x capital N, given the condition that a capital N is equals to small n and corresponding probability capital N is equals to small n. So what we are conditioning on the capital N, we are saying that capital N is equals to small n. So if you put this condition in the next line, it will boils down to sum over n from 0 to infinity, expected value of s to the power x1 plus x2 plus xn small n, and probability n equals to n. Now so far we have learned that if these x1, x2, xn, if they are independent, then the PGF of the sum of these random variables will be product of their individual PGFs. So here we have n such independent random variables, so we have n such probability generating functions, and we know they are following a common probability generating function Pxs. So it will be Pxs to the power n into probability n equals to n, and sum over n from 0 to infinity. If we see the form, it is something s to the power n into probability n equals to n. So once again this is a PGF and this is for capital N. So it will be P capital N, this is the suffix, it says that this is the PGF of capital N, so Pn Pxs. So this is the form that we want. Now if we differentiate this function P Sns once, what we'll have? We'll have P prime Sns as P prime N Pxs and P prime Xs. This is what? Because if this can be considered as f of a function of another function. So the argument of this function is itself as a function. So if we want to differentiate, first we have to differentiate the first function, then we have to differentiate the function which is acting as an argument of that function. Now we put s is equals to 1. So what we'll have? P prime Sn 1. So if we put s equals to 1, we have P prime N Px1 and P prime x1, and we know that Px1 is 1, so it boils down to P prime n1 and P prime x1. So that is expected value of Sn can be written as expected value of n into expected value of any of the random variables. So if we use these concepts, then we can find the variance also. The form of the variance, which can be after doing some mathematics, can be shown. Variance of Sn is equals to expected value of n into variance of x plus variance of n into expected value of x square. Now we consider a special case called compound Poincare distribution. Suppose that this capital in this random number follows Poincare distribution with parameter mu, and x1 is once again Poincare distribution with parameter lambda. Then the PGF of Sn, if we follow this definition, Sn is capital N, this is the random number of variables, then the PGF of Sn will be e to the power minus mu into 1 minus e to the power of minus lambda into 1 minus s. We can consider one example. Suppose this is a funny example we have, that a hen lays n capital N eggs, where capital N follows a Poincare distribution with parameter lambda, and each egg hatches with probability P independently of the other eggs. Now we are to find the probability distribution of the number of chicks, capital Z. So here we have capital Z as x1 plus x2 plus x capital N, where each of the xi's they follows a Bernoulli with P, because each egg either hatches or not. So we have dichotomous random variable, and we have the success probability as P. So each of the xi's follows Bernoulli distribution with P. In that case, P and S will be e to the power lambda s minus 1, and Px1 will be q plus Ps. Now another example, suppose Qj is something like that, probability x greater than j. So this is Pj plus 1 plus Pj plus 2 and so on. And we define Qs sum over j from 0 to infinity Qj s to the power j. So this is once again some sort of generating function. Then Qs can be written as 1 minus Ps over 1 minus s whenever s is less than 1. The proof is not very rigorous. Qs by definition is from j from 0 to s, Qj s to the power j. Now by definition of Qj, this is pk sum over k from j plus 1 to infinity. So right now we have two summations, one j from 0 to infinity, one k from j plus 1 to infinity. Now if we combine these two ranges, then this is equivalent by saying j ranges from 0 to k minus 1 and k ranges from 1 to infinity. If we do the interchange, then we are left with sum over k from 1 to infinity pk, and this is a geometric series 1 minus s to the power k by 1 minus s, because s is less than 1. So this is nothing but 1 minus ps by 1 minus s. So if we know this form, then expected value of x can be written as p prime 1, which is equivalent by saying q1. If we say q1, this is nothing but k from 0 to infinity qk, and once again if we put the definition of qk, we'll have two summation, and once again if we interchange the range k and m, then we'll be left with sum over m from 1 to infinity mpm. This is nothing but the expectation, or p prime 1. Through this module we have learned, or we have got an idea about the concept of probability generating function, how this function can be used to find the probability mass function, or given a probability mass function, how to get the probability generating function has also been discussed. One very important property is the sum of random number of independent random variables has also been discussed.